In this video, we're going to talk about the cell potential and equilibrium. Think to a voltaic cell again. We've got our solutions, we've got our solids and solutions, we have ions on both sides. We discussed this briefly when we talked about changing voltage over time as the reactants get used up when we introduced Gibbs energy relation to cell potential. Let's take a closer look at it. Really, the idea is if I have a bunch of things like copper, and I have a bunch of copper ions, on the other side I have a bunch of zinc and a bunch of zinc ions. Well, all of these are bouncing against their metal all the time. The ions are moving and can bounce in. The copper's doing this as well all the time. More often than not, because copper wants electrons more, as the electrons are moving through and kind of sloshing all over. Remember that they're fairly fluid. We literally talk about the sea of electrons. They are loosely associated in a metal. They're not really tied to any one atom. And so electrons are coming on and off kind of all the time. There's plenty of instances where a zinc will stick to the metal and become just zinc. It won't be an ion anymore. Electrons will flow into it from the surrounding area. This leaves little holes that other electrons need to flow to fill. That leaves a hole. And in the end, you can pull electrons possibly all the way over from the copper. It's possible occasionally for a bit of copper to break free and become copper 2+. But this is not favored. Copper wants electrons more. It pulls more strongly. Over time, the spontaneous reaction favors the copper gaining the electrons. And as a result, we don't really expect that many to break free. We expect instead a lot more of them to stick to the surface over time and cause more of our zincs to break free and become zinc 2+. Nonetheless, there is a back and forth. And as you get less and less and less copper 2+ remaining and more and more and more zinc 2+, or whatever your oxidized species is, there's just many more impacts where zinc is trying to obtain an electron. Say zinc was 1/10 as good at getting the electron as the copper. If you have equal numbers, then copper is going to get it 10 times more than the zinc solution does. But if you have 10 times more zinc, well, now they're about equal. For every one copper that steals it, you have 10 zincs that try, and, well, they do it 1/10 as often, but that still means it's 1 copper for 1 zinc. And if you had 100 times more zinc, well, then you'd actually be pulling the electrons towards the zinc more. If you pulled the electrons towards the zinc more, the zincs would start going away. They'd start getting consumed and more copper would show up. Until eventually the fact that there's more of these around would favor it going back. This will reach an equilibrium. Electron transfers are actually equilibrium electron transfers. Really, every reaction is an equilibrium reaction, but so far we haven't really discussed electron transfer in that light much. While there is a very heavy preference for electrons to transfer towards one element versus another, depending on the difference in their potential, nonetheless, you can, through mass action, get some of them going the other directions, which means you'll never really use a voltaic cell to its limit. You'll never really use a battery to its limit. It will stop somewhere earlier when you reach an equilibrium of transfer between the two species. Well, we know that the free energy, the Gibbs energy, is equal to the negative moles Faraday constant voltage of your cell. But if we think back to Gibbs energy, that was equal to the negative RT ln of K. Your standard Gibbs energy was equal to the negative gas law constant times 298 times the natural log of the equilibrium constant. Well, assuming that we're reasonably at standard states for our cell, 1 molar or 1 atmosphere, then we can relate these two. Negative RT ln of K must be equal to negative NF E cell, which we can rearrange so that the E cell, or voltage of our cell, is equal to RT over NF times the ln of K. If we want to plug in a bunch of values here at 298, we can then determine that the voltage of a cell at standard state conditions is going to be equal to 0.0592 volts per moles of electrons being transferred in the reaction times the log of K. And so we went ahead and converted our natural log to log, which is just done often in these situations, as that's how the Nernst equations that we'll end up at eventually is written. This actually allows us to use the free energy relations to create a relation between the voltage of a cell and the equilibrium constant for the electron transfer. So let's take a look at our standard one so far, our zinc-copper. So our zinc-copper relation has a 1.10 volt potential for our zinc 2 plus aqueous, our zinc solid, copper solid, copper 2 plus aqueous solution, voltaic cell. So 1.10 volts must be equal to 0.0592 volts per mole of electrons, log of the equilibrium constant. Rearrange this for a second. 10 to the 1.10 volts divided by 0.0592 volts times the moles of electrons on top is going to be equal to our K. And the moles of our electrons that we're transferring, zinc 2 plus, copper 2 plus, zinc 0, copper 0, we're moving 2 electrons. So our N is going to be 2, which is going to give us 10 to the 2.2 divided by 0.0592 is equal to K, which tells us that 10 to the 37.16 is equal to our K. So that our equilibrium constant is 1.45 times 10 to the 37. That is enormous. This is very much in favor of the products. Very, very little starting material. Well, our zinc plus our copper 2 plus was becoming copper solid and zinc 2 plus. So we have an enormous amount of copper and zinc ions, and we have very little zinc solid and copper ions. Why is it so large? This is an enormous equilibrium constant. Well, if we think about it, electrons are really easy to move. They're small, they get really close to the nucleus, they hold on to the atom. It's not like a molecular reaction where you're holding on to another atom at a much greater distance. Electrons, when they go on to the charged ion metal, get much closer to that metal. It's harder to get them back off. They're a more difficult thing to remove than, say, an N2O4 in equilibrium with two NO2s. So the nature of the attraction that we're dealing with is just very different than when we think about molecular equilibrium. Electron transfer equilibrium tend to be very heavily one-sided. But nonetheless, it's not nothing. And the closer your potentials, the smaller your voltage, the closer that equilibrium will become. Fortunately, though, as long as we're running a reasonably good voltage, practically all of our electrons transfer. The absurdly tiny amount that doesn't isn't even going to be noticed by whatever application we're applying it to in normal everyday life.